Hey guys, and welcome to Disha and Avani's fantastic calculus class, where Leibniz's or Newton's boring theories are funified. Disclaimer.
Our problem today involves a 100 centimeter string. Our purpose is to use the 100 centimeters of string to produce a circle and a square with the maximum area. Where should the cut be made to maximize the sum of areas of the circle and the square, and to minimize the sum?
But there are so many ways the wire can be cut. Our goal is to find the exact place where the cut should be made. What should we do?
Here is a quick visual of the problem. We have to find a way to maximize and minimize the total area of the two shapes. How do we do this?
Good old differentiation. Let's begin with what we know. Put out the circumference/perimeter and area formulas from memory.
We know that the total string available is equal to the circumference of the circle plus the perimeter of the square. Therefore, our first equation is 100 equals 2 pi r plus 4w. We also know that the total area equals the area of the circle plus the area of the square. And we have our second equation, area equals pi r squared plus w squared. Note, this equation is what we're trying to maximize and minimize. What is next? Let's use these babies.
Because we have two variables, radius and the side of the square, let's choose one variable to isolate.
Over here, we isolated the side of the square. And what you see right here, by the way, is the side of the square isolated relative to the circumference of the circle.
Finally, we find our function AR.
So what we did here was we substituted the w into the area function right over there. And we have our AR function. What's this? A moment of realization. Aha, the equation is a quadratic relationship. You know what that means. One vertex.
Next, we find the derivative.
Remember the chain rule? Once we have our derivative solved, we have to make it equal 0.
Making the derivative equal 0 will give us a max or a min. Remember, it is a quadratic function, people.
So the reason on paper is explained this way. We know that the area function is a quadratic relation. Therefore, it looks something like a parabola. And we know that a prime is the slope. So the pink lines that you see on the camera are just various of the tangent lines possible on this function. So note here that where the function a prime equals 0 is where the minimum point of the function AR is. That point right there. So this is our minimum value. A prime equals 0 at r equals 50 over 4 plus pi. Refer back to a prime equation if you do not understand how we got this value.
Yay, we passed the first hurdle and found three critical points at 0, 50 over pi, and 50 over 4 plus pi. Wait, what?
Sigh, let me explain. So remember what critical points are. Critical points exist where the derivative of a function equals 0, where the derivative of a function does not exist, and the end points. Let's review the question. 100 centimeter of string. This is a restriction. Our domain is not of all real numbers. So, our domain is r is greater than or equal to 0, and it's less than or equal to 50 over pi. How did we get this number? Well, the circumference of a circle is 2 pi r, and we know that the maximum amount of string we have available is 100 centimeters. Thus, we know that r is going to equal 50 over pi at the most.
We use the second derivative to find out if the point at a prime equals 0 is a max or a min. We get a positive number. Therefore, it is a min.
Referring back to the parabola that we drew a while back, we can also figure out that it is concave up. And when it's concave up, the minimum point is the minimum point. So what we do next is we find the coordinates. Plug in our critical points into the area function, equation number 2, to find the area at each of those points. So A at 0 is equal to 625. So our first point is at 0 and 625. Second critical point was at 50 over pi. When you plug that into the area formula, we get around 796. So our coordinates are 50 over pi, 796. And our third critical point was at 50 over 4 plus pi. When you plug that into the area formula, you get about 350. So our coordinates are 50 over 4 plus pi, 350. We're almost done, my little unicorns.
Let's quickly take a glance at the graph. To minimize the sum of areas, we use the absolute minimum point on the graph.
So once we have all three of our coordinates plotted on the graph, we can easily see which is the minimum, which is the maximum, and which is the local maximum in this function.
For a minimum sum of areas, the cut should be made at 44 centimeters.
And we figured that out by plugging in our minimum, our coordinate, right into the circumference formula. That gave us the distance around the circle, the smallest circle, in other words.
To maximize the sum of areas, no cut should be made, and the string should only be used to make a circle.
We know this because the greatest amount of area that is possible is if the total string equals the circumference of the circle.
The minimum area is 350 centimeters squared, and the maximum area is 796 centimeters squared.
The question didn't ask for this, but we can figure this out because on the graph right here that we showed you a moment ago, we can see that the maximum area is 796 and the minimum area is 350. See, my little pixies, it wasn't so hard. Now you shall never look at strings the same way again.
We are done. Hope everyone gained some calculus wisdom today.